Hi everyone, welcome back to Chem Help ASAP. In this problem set video, we are going to do problems where we write chemical equations that include states. Then we are going to talk about the different ways to measure concentration. After we are comfortable with concentration, we are going to use those concentrations to work on colligative property problems. So we're going to change up boiling points and freezing points. Then we're going to take a look at our solubility rules. And using those solubility rules, we are going to write molecular, complete ionic, and net ionic equations. And then finally, we will do some problems where we will do stoichiometry using concentration. Let's get started. Let's first practice writing chemical equations where we have not only our reactants and our products and we've balanced everything, but also let's put states in. So this problem reads, solid zinc metal reacts with aqueous hydrochloric acid to form hydrogen gas in an aqueous solution of zinc 2 chloride. Write a balanced chemical equation including states for this reaction. Looks like we are also going to have to use our naming rules to get everything in. Let's start with our reactants. So we have solid zinc metal reacting with aqueous hydrochloric acid. Okay, those are our reactants. So zinc metal is just Zn for zinc. I'm going to give myself some space here. Plus we're reacting with hydrochloric acid, which they gave us. So that's just HCl. Make sure there are no more reactants. No, because now we're going to form hydrogen gas. So we're moving to products. Give myself a little bit of space here. Okay, so we are forming hydrogen gas. That is H2. And we are forming an aqueous solution of zinc 2 chloride. If you need to, go back and review your naming rules, but zinc 2 chloride will be this molecular formula. Okay, we have our reactants, we have our products. Next, I'm going to go ahead and balance. Our zinc is fine, but our hydrogens and chlorides are not. So balancing chlorine, I'm going to put a 2 here, and that takes care of my hydrogen as well. Okay, fantastic. I have a balanced equation, but I have not yet put in states, so let's put in states. For zinc, it said I started with solid zinc metal, so I simply need an S here. I reacted it with aqueous hydrochloric acid, so let's put an AQ by hydrochloric acid. For the products, I formed hydrogen gas, okay, so I need a G here, and another aqueous solution, so I need an AQ by my zinc chloride. And now I have a balanced chemical equation with all of my states. Let's do one more. This problem reads, aqueous sodium hydroxide is neutralized by aqueous sulfuric acid. Pure water in an aqueous solution of sodium sulfate is formed. Write a balanced chemical equation including states for this reaction. Okay, let's get reactants and products in. So we're starting with aqueous sodium hydroxide. So sodium hydroxide. We are reacting it with sulfuric acid, which they gave us. That's great. Any more reactants? No, now we go on to what we formed. So we formed water and an aqueous solution of sodium sulfate. Any more products? Nope, it looks like that is it. Now let's balance. I notice right away that my sodiums are not balanced, so let's put a 2 here. Okay, now sodiums are balanced. I'm going to hold off on hydrogen and oxygen till the end. Let me check my sulfurs. See, 1 here and 1 here. Okay, so sulfur is balanced. Now I need to check hydrogen and oxygen. Next, let's do hydrogen. Let's see, 2 times 1, I have 2 hydrogen here, plus 2 hydrogen here. I have a total of 4 hydrogen on my reactant side, and on my product side, I only have 2. Let's balance that. Now I have 4 on both sides. Now let's check oxygen. Again, I have 2 and 4. That gives me 6. I also have 2 here and 4. That gives me 6. Okay, so I have a balanced chemical equation. Finally, let's put in our states. So the problem said that sodium hydroxide was aqueous. So that is an AQ there, and it reacted with aqueous sulfuric acid. So we have another AQ. Now pure water was formed. Pure water is a liquid, so we'll put an L here. And we're forming another aqueous solution, so our sodium sulfate is AQ again. And there is our balanced chemical equation with states. Here is our first problem. We are dealing with vodka, which is actually an aqueous solution of ethanol and water. So the problem tells us that our concentration of ethanol is 0.68, and it's in molarity. If we want 1 mole of ethanol, how many milliliters of vodka do we need? Since we were given molarity, let's get the equation for molarity up. Now let's start plugging in the numbers that we know. We know our concentration was 0.68. We know that we want 1 mole of ethanol. Using this, we can actually calculate our liters of solution, which is, in this case, is our liters of vodka. So doing a little simple algebra, we get 1.47 liters of solution, or liters of vodka. Now, our problem did not ask us for liters, but asked us for milliliters. So a simple conversion from liters to milliliters, we need 1,470 milliliters of solution. Let's do another concentration problem. Now we want to know the concentration of a brine solution. We have dissolved 225 grams of sodium chloride in 0.85 liters of solution. Well, to calculate molarity, we are going to need moles, and we were given grams. So our first step is going to be converting those grams into moles. So I simply use my molar mass. Here are my 225 grams of sodium chloride. Make sure those cancel, and I get 3.85 moles of sodium chloride. Now, using my equation for molarity, I can start plugging in what I know. I just calculated my moles of sodium chloride. The problem told me I needed 0.85 liters of solution, so I can calculate molarity. Plugging this into my calculator, I get a molarity of 4.5. Okay, but what if we want to know how many grams to dissolve? So this problem reads, how many grams of ammonium nitrate are needed to make 350 milliliters of a 0.2 molar solution, or 0.2 molarity? Just like before, here is our equation for molarity. Let's plug in what we know. We know the concentration. We want to make a 0.2 molar solution. We know how much we want to make. Now notice here I converted my 350 milliliters into liters. It's just a matter of moving the decimal, but make sure these units are liters here. I can calculate how many moles of ammonium nitrate I need. So I am going to need 0.07 moles of ammonium nitrate. I also went ahead and put in the molecular formula for ammonium nitrate because of course I have moles and the problem has asked me for grams. My final step is to take my moles of ammonium nitrate, use the molar mass, making sure my moles of ammonium nitrate cancel, and I get 5.6 grams of ammonium nitrate. Molarity is very commonly used, but there are some other ways of measuring concentration that are still used just a little less commonly. Let's take a look at a problem with molality. This problem reads, how many grams of lithium bromide are needed to make a 1.5 molality solution in 0.75 kilograms of water? So let's get the equation for molality up. Here it is, and let's plug in what we know. We know the concentration is a 1.5 molality solution. We know our kilograms of solvent. In this case, our solvent is water, so let's put in those 0.75 kilograms of water. Okay, so we can actually calculate our moles of lithium bromide. Again, notice that I put it in a molecular formula. So doing a little bit of algebra, I get 1.13 moles of lithium bromide. That's great, except my problem asked for grams. So let's do a moles to gram conversion. Here are my 1.13 moles of lithium bromide using molar mass, making sure my moles cancel, and I'm left with grams. I get 97.7 grams of lithium bromide. And let's do one problem where we measure concentration in terms of percentages. So the volume percent of household vinegar is usually 12.5%. If you have 50 milliliters of household vinegar, how many milliliters is pure vinegar? So let's get our equation for volume percent up. Here it is. It is simply the volume of our solute over the volume of our solution. So let's plug in what we know. We know our volume percent, our concentration is 12.5%. Now in terms of knowing solution and solute here, let's just plug in what these actually are. So our volume of solute is our volume of pure vinegar. Vinegar is actually our solute. Our solution is our volume of dilute vinegar. Now we can get some other numbers in. Our 12.5% stays the same, but we know that we have 50 milliliters of our dilute solution of our household vinegar. Now we can calculate how many milliliters we have of our pure vinegar. So some simple algebra, and we have 6.25 milliliters. Now in terms of your units of volume, they must match, but it doesn't matter what they are. Because I had milliliters of dilute vinegar, that gave me milliliters of pure vinegar. If I started with liters of dilute vinegar, that would give me liters of pure vinegar. I could even measure in something crazy like fluid ounces. Just as long as my units match, I'm totally fine. Now let's apply our concentrations to colligative properties. So if you have ever cooked pasta, you've probably put some salt in the water. Let's see if adding salt to your pasta water will actually help it cook faster by raising the boiling point. So in this problem, we have added 5 grams of sodium chloride. That, of course, is just table salt. And we have a pot that has 4 kilograms of boiling water. What we want to know is what is the new boiling point of this water. To calculate a change in boiling point or freezing point, we are going to need to know the concentration of the salt in that water. And specifically, we are going to need to know that concentration in molality. So our first step is going to be converting grams into moles. You have probably noticed in this course that converting grams into moles or moles into grams happens quite often. So taking my 5 grams and using my molar mass, here my grams cancel, I actually have 0.086 moles of sodium chloride. Now using my equation for molality, I'm going to plug in what I know. Here is my 0.86 moles of sodium chloride, which I just calculated. The problem told me that I have 4 kilograms of solvent, in this case 4 kilograms of water. So my molality for this solution is 0.021. Now that I know my concentration, I can calculate how much my boiling point has changed. So here is my equation for my change in boiling point. Let's also get a table with some physical constants here. For this problem, I am only interested in water because I'm not working with chloroform or ethanol. In my equation, I see I'm going to need the constant for the boiling point elevation, or Kb. Here it is right here. Now you probably already know that the boiling point of water is 100 degrees C, but it is in my table just in case you've forgotten it. So let's calculate how much the boiling point of water changes. So here is my Kb, which of course I got from my table. I calculated my concentration already. It's 0.21. And that is in molality. So I know my boiling point is going to change 0.011 degrees Celsius. That's not very much. So in terms of water, because I started at 100 degrees C, that is my boiling point, I am only going to add 0.011 degrees C to that boiling water. So my final boiling point is 100.011 degrees C. I don't think my pasta is going to cook any faster, but maybe it'll have better flavor. Let's take a look at a changing freezing point. So ethylene glycol is added to car radiators to keep them from freezing in the winter. You have probably done this. If the temperature overnight is expected to be negative 9.5, what concentration of ethylene glycol should be in the radiator? So we need to change the freezing point of the water in the radiator. Let's get my table with my constants up. I'm still just working with water here, but this time I need my constant for my freezing point depression. And again, just as a reminder, the freezing point of water is 0 degrees C. So we need to be able to bring this down to negative 9.5 degrees C. So using my equation for a change in freezing point, here it is right here. We have our constant. We would like to know our concentration. How much is our freezing point going to change? Well, the nice thing about having water is, of course, the freezing point is at 0 degrees C. So if we're going down to negative 9.5, our freezing point has changed by 9.5 degrees. So plugging in, our change in freezing point is 9.5 degrees. Notice it is a positive number. It's simply the change, how many degrees it has changed. Here is our freezing point depression. Again, I got this off of the table, and we just need to calculate our concentration. This is simple algebra. So our concentration of ethylene glycol for this very cold night should be 5.1, and that is measured in molality. Let's switch gears a little bit and let's talk about solubility rules. So here is a table that summarizes our solubility rules. And let's determine if different salts are soluble or insoluble based on these rules. Our first salt is potassium carbonate. First, I'm going to check out the cation. In this case, my cation is potassium, and I see I have a rule that includes potassium. The alkali metals are soluble, and there are no exceptions. So right away, I know that potassium carbonate is soluble. However, what if you had looked at rules for carbonate? So here is carbonate. It is a mostly insoluble ion. However, it does have some exceptions, and one of those exceptions is potassium because it is an alkali metal. So either the cation or the anion would lead you to the same conclusion, yes, this is a soluble salt. Next, let's do aluminum phosphate. So looking for aluminum. In my rules, I'm not really seeing much about aluminum. So let's switch and let's take a look at phosphate. Okay, I do have rules for phosphate here. This is a mostly insoluble ion. Here are my exceptions. Do I find aluminum in the exception? And I do not. Therefore, aluminum phosphate, insoluble. Next, let's look at magnesium hydroxide. So seeing if I can find magnesium in my table, and I am not seeing magnesium. So let's check out hydroxide. Okay, I do have a rule for hydroxides. Again, it's an insoluble salt. Let's see if magnesium is maybe an exception. My alkali metals are exception, as well as ammonium, and then calcium, strontium, and barium, but no magnesium. So therefore, magnesium hydroxide is insoluble. Let's take a little twist on our solubility rules. You need to form an insoluble salt that contains the chloride anion. Which salt or several salts should you form? So this is pretty common in water purification. You might need to remove a certain ion. So in this case, we want to remove the chloride ion. So if I find my rules for chloride, here we go, they're with the halogens. You see that chloride is a mostly soluble ion, but we want to form something that's insoluble, so we want to look at the exceptions. And I can see there are 3 exceptions for the chloride ions: silver, mercury, and lead. So I have 3 insoluble salts that I can form with chloride: silver chloride, mercury chloride, and lead chloride. Let's continue using our solubility rules, and let's start writing ionic and net ionic equations. So our problem states that we want the molecular, complete ionic, and net ionic for the reaction of ammonium hydroxide, potassium acetate, and that's going to form ammonium acetate and potassium hydroxide. Let's get the molecular equation first. So ammonium hydroxide, that is going to be NH4OH. Let's check and see if this is soluble. So I do have a rule on the cation, the ammonium. It is a soluble salt. There are no exceptions. So I know that ammonium hydroxide will be aqueous. Let's take a look at potassium acetate. That is going to be K3O2. Let's check solubility rules, and let's see if this is going to be soluble or insoluble. I do see potassium here under soluble and also acetate under soluble. They both have no exceptions, but this is definitely a soluble salt. Next, we have ammonium acetate. That is going to be, wow, it's going to be a long one. Let's see if it's soluble. Again, we know that ammonium is soluble and also acetate, so yes, this is definitely soluble. And for our last one is potassium hydroxide. Checking our rules to see if this is soluble. Well, we're still working with potassium and there are no exceptions, so yes, this is soluble. Now we can write our balanced molecular equation. Here it is right here with the states. And we're ready to go to our complete ionic equation. So every salt that is soluble or has an AQ next to it, we are going to break apart into its cation and anion. So ammonium hydroxide becomes ammonium and hydroxide. Potassium acetate becomes potassium and acetate. For our products, ammonium acetate becomes ammonium and acetate, and potassium hydroxide also becomes potassium and hydroxide. So because all of my salts were soluble, everything was broken apart into cations and anions. So finally, to get our net ionic equation, we want to remove all the spectator ions. Now these are ions that are same on the reactant and product side. So let's start canceling. Ammonium is the same. We do have hydroxide. What about potassium? Let's see. Yes, it's here and here. Acetate also is a spectator ion. Everything is a spectator ion. This means for our net ionic equation, we usually write NR, meaning no reaction. There is no net ionic equation because everything is soluble. Let's do a solubility problem where we definitely have a precipitate. This problem reads, one way to remove mercury from water is by precipitating it out. If you have a water sample with mercury ions, what salt would you add to precipitate the mercury? And we want to write the net ionic equation for the reaction. Let's first look at the solubility rules for mercury. I'm not finding a rule for mercury on my left-hand column here, but I am seeing mercury here under my exceptions. So if I have mercury as a cation, I can either have a chloride, bromide, or iodide anion, and that will make an insoluble salt since mercury is an exception here. So I want to add something with a chloride ion because that will form an insoluble salt with mercury. Now we can use just about any chloride salt. What if we just use table salt? Remember, table salt is just sodium chloride. That will give us chloride ions because it is a soluble salt, and that should form an insoluble salt with mercury. Let's add table salt to the water. What would our net ionic equation be? We know we have mercury ions in the water. We've added table salt to add chloride ions, and we will form mercury chloride as a result. And that will precipitate out all of the mercury. Of course, we can't have balanced chemical equations without doing stoichiometry. So let's bring all of this together and do a stoichiometry problem. How many grams of precipitate will form when excess magnesium nitrate reacts with 350 milliliters of a 1.65 molar solution of potassium sulfide? The product of the reaction are magnesium sulfide and potassium nitrate. Of course, we need to get a balanced chemical equation with our states so we know what is soluble and insoluble. Looking at all the salts in our problem, using our solubility rules, let's figure out what's soluble, what's insoluble. Magnesium nitrate. We know that all the nitrates are soluble. So that means magnesium nitrate is soluble as well as our potassium nitrate. What about our sulfides? We have potassium sulfide and we have magnesium sulfide. Well, I already know that potassium forms all soluble salts. There are no exceptions. So my potassium sulfide is going to be soluble. My magnesium sulfide, however, is not going to be soluble. We can double check this with our sulfide rules. You can see that magnesium is not one of the exceptions. So that is going to be our precipitate. Here is our balanced chemical equation with our states. And you can see magnesium sulfide is specified as a precipitate. As usual, when we are doing a stoichiometry problem, we need moles. The problem gave us a volume and a concentration, so we need to use these pieces of information to get us to moles. Let's first get up our equation for concentration. Now let's plug in what we know. We know our concentration is a 1.65 molar solution. We also know how much of it we have. We have 350 milliliters. Now, remember, this is liters of solution, so we just need to make a quick conversion, and we have 0.35 liters of this solution. That allows us to calculate our moles of potassium sulfide. So we have 0.578 moles of potassium sulfide. Okay, great. We know how many moles of our reactant we have. Our problem asked us how many moles of our magnesium sulfide or our precipitate is going to form. Now we need to use our mole ratio. Rewriting the 0.578 moles of potassium sulfide. Using my mole ratio, which in this case is just 1:1, which is fabulous, we get 0.578 moles of magnesium sulfide. Notice, however, though, that my moles did cancel, so I have moles of magnesium sulfide. Now that I know moles of magnesium sulfide, I need to convert to grams. So rewriting my moles of magnesium sulfide, using the molar mass, making sure my units cancel, I get 32.6 grams of magnesium sulfide. Now, if you prefer, you can calculate this 32.6 grams of magnesium sulfide in one long calculation. I will show it to you, but again, choose whichever method makes the most sense. Starting with my 350 milliliters of solution. I first convert from milliliters to liters. Then I'm going to use my concentration as a conversion factor. Notice my liters of solution cancel and I'm left with moles of potassium sulfide. To convert to moles of magnesium sulfide, here's my mole ratio. Always love it when it's 1:1. My units cancel. Now I have moles of magnesium sulfide. And my final step is simply to convert to grams of magnesium sulfide. So again, I make sure my units cancel. I'm left with grams of magnesium sulfide. And my final answer again is 32.6 grams of magnesium sulfide. Let's do one more precipitation problem. This one reads 0.15 grams of calcium sulfate was isolated from the reaction of calcium chloride and sodium sulfate. The other product is sodium chloride. What was the original concentration of sodium sulfate if 75 milliliters was initially used? First, let's get a balanced equation. If calcium sulfate was isolated from the reaction, that's definitely a product. Our problem also specified that sodium chloride was our other product. So our two reactants in this case are our calcium chloride and our sodium sulfate. If calcium sulfate was isolated, it probably means that's the precipitate, yes, but let's double check our solubility rules. So here are our sulfate rules. They are mostly soluble, except you can see calcium is an exception here. We can also check our other salts. Calcium chloride, remember chlorides are mostly soluble. Calcium is not an exception. Sodium sulfate, sulfates are mostly soluble, and sodium is not one of my exceptions. And of course, table salt we know is soluble simply because chloride salts are soluble and also sodium salts are soluble. Here is our balanced molecular equation. And notice I put our calcium sulfate as our precipitate. Okay, stoichiometry, moles, moles, moles. Starting with our 0.15 grams of calcium sulfate and using the molar mass, cancel, cancel, we get 1.1 times 10 to the negative 3 moles of calcium sulfate. Now that we have moles, we can use this to predict our reactants in this case. Remember, we wanted to know the original concentration of sodium sulfate. Rewriting my moles of calcium sulfate using my mole ratio, which is another fabulous 1-to-1 mole ratio, I get 1.1 times 10 to the negative third moles of sodium sulfate. Fantastic, I have my moles of sodium sulfate. Do I need to go to grams? Well, if I go back to my problem, I want the concentration. I'm going to want to stay in moles because here is my equation for concentration, and notice I need my moles of solute. Now, if you're ever doing these problems and you've gone ahead and converted to grams, that's fine. You still have your moles. Just make sure you use your moles and not your grams. You've just done a little bit of extra work. Let's plug in the numbers I know. I've already calculated my moles of sodium sulfate. The problem told me that I had 75 milliliters initially. Again, make sure you convert this to liters. So that is 0.075 liters of solution. So I have a concentration of 1.47 times 10 to the negative 2. I will also show you how to do this problem in one calculation, starting with my 0.15 grams of calcium sulfate. First, I convert to moles. So grams cancel, and now I have moles. Then I use my mole ratio to convert from moles of calcium sulfate to moles of sodium sulfate. Again, making sure that cancels. And then finally, I simply need to divide by my liters of solution so that I have moles of sodium sulfate over liters of solution, and I get 1.47 times 10 to the negative 2 once again. As I have said before and will continue to say, use the method that makes the most sense to you. I hope working these problems helped you, and thanks so much for watching.